Continue talking about rotation as we were talking about the other day. And I finished off by briefly mentioning some things about angular graphs. So I'll talk about that today. And then we'll talk more about what's in section 6.2. We'll talk more about centripetal acceleration. And we'll also talk a little bit about dynamics of circular motion as well, depending on how far we're able to get within an hour of my yapping voice. So when we're able to determine that, we can then move on. Okay. So we also talked a little bit about revolutions and things like that. So to recap what I talked about in our first lesson, very quickly, we defined a few quantities. Let's get our whiteboard out like that. And let's put it out like that. There we go. To quickly recap what I talked about in the lesson, so the recap, we defined a few quantities. We defined the radian angle as the ratio of arc length to its radius. And this is the definition of a radian. Right? And also we defined angular velocity or angular speed. And remember, this is the Greek letter omega, and not to be confused with W. And this is okay. We define angular speed. In addition, we defined the unit changes between we defined our unit change. We defined, of course, there's going to be 1 revolution is equal to 2 pi radians, which is, of course, is equal to 360 degrees. We defined that as well. Also, lastly, we briefly mentioned this change in theta equation, this manipulated equation. Delta theta is equal to theta final minus theta initial equals angular speed times the change in time. Okay. And we define this equation, which is really just a manipulation of the top equation here. But we'll talk more in angular kinematics later. Okay. That's our brief recap of what we did last time. So, talking about graphing. So, just like in linear motion, we have, of course, their famous position time graphs, and then we have our velocity time graphs, and then we have, of course, our acceleration time graphs. And of course, in this situation, we have the slope of the line is equal to the speed of the object. And in this situation, we have slope of the line is, of course, equal to its acceleration, and the area under its curve. And we have the area is equal to its position. Okay. Lastly, of course, the acceleration time graph. Acceleration time graph measures the jerk. The slope of it measures the jerk. We don't talk about that much about that, but we do know the area under an acceleration time graph is velocity. Similarly, we have the same situation for our angular motion, which we'll talk more in detail about. We have our theta position time graph, and of course the slope is equal to its angular speed, and then we have its position time graph, angular velocity time graph, where it's represented. The slope is what we call the angular acceleration, represented by Greek letter alpha, and of course, the area is of course equal to its angular position. And the same holds true for its angular acceleration time graph. The angular jerk is measured here, and this area is of course its angular velocity. But we'll go into more detail about that later. In the ideas that we learned about measuring the increasing, right? Here we have the slope is increasing, which remains constant on a velocity time graph. The same principles hold when we talk about angular motion. In this situation, it increases. To describe this graph on this graph, here I would need a different color. Let's use, let's use blue to describe it. Here, in this situation, I'm going to use blue. To describe it on the linear time graph, I'll use red on the angular time graph. Right? That describes what happens when there is a constant increase in the angular velocity. It ends up staying exactly the same. Okay. So the same rules apply when you're talking about angular motion. And for more detail, you can go back and study on the graphs when I talk about it. Now, so let's do an example involving these graphs, and you'll kind of get the gist of what I'm trying to tell you. Mm-hmm. And of course, my victim child is named Helen, so that's who we're going to talk. So that's who this problem will be named after. So here's the example. Find the following. Okay. So I'm going to draw her angular speed graph. And I'm going to draw her position graph, something like that. Okay. It is basically kind of to scale as much as I can make it. Okay, so her position, so her angular position time graph is like that. Okay. Okay. So our solution for this problem let's go on a new page. So the solution for the problem here is to first understand what the F we're talking about. So we know, so we're given the graph here, and we go back to the third board right here, we can see what? We can see it starts at time 0. This will be assumed to be time, starts at the origin at time 0, and it's increasing till about 70 seconds right here. Okay, so we can see that. Let's go back to page 4. So we can see the solution first is to understand what we're doing. Since in this situation everything's given in a graph. Normally we do known and unknowns, but not in this situation because, well, that's not given. So we can see the fact that we have a constant increase there's a constant increase from 0 seconds to 70 seconds. Alright, so it's going. Of course, if I'm looking at it, and it's going from 0 to 3 pi divided by 4. Okay. Constant increase. And then, the angle changes. Theta at time 0 to the 0 radians. Theta at 70 seconds is, of course, 3 pi divided by 4 radians. Then I know also that it does not increase. There's no change. In other words, there's no change from 70 seconds to 100 seconds. So that is to say, your theta at 70 is equal to theta at 100, which is 3 pi divided by 4 radians. Okay. So interpreting that, understanding what that means, on our velocity time graph, we're going to have a constant at we're going to have a constant of 3 pi divided by 4 until we get to 70 seconds, where it goes down to nothing. How do I know that? Okay. Simple. The slope of the position time graph of its angular velocity. So the angular velocity is measured at from 0 to 70 seconds. Is of course the change in the angle over the change in time, which is of course 0 to 70 seconds. So this is going to be 3 pi over 4 minus 0 over 70 minus 0. So 3 pi over 4 times 1 divided by 70. Okay, that becomes 3 pi over 280. Which I can just leave with that. So it's omega. Omega is of course 3 pi divided by 280 in radians per second. That I know. Now, there happens to be no change in angle for the other one. Right? The omega from 70 to 100 is delta theta over delta t, which is 3 pi divided by 4 minus 3 pi divided by 4, because the angle does not change, over 100 minus 70, which is, of course, you mathematicians are wonderful and are really smart, know this is 0 radians per second. Okay, so I have two answers to work with here. So I know that when I graph it, I'm going to have it at 3 pi divided by 280, whatever the hell that is. Then I'm going to have it at 0. Now, for the sake of simplicity and for the sake of you being able to actually see what's going on, we're going to draw the scales a little bit bigger. Okay. So we have from 0 to 70, which is right about here. And we can make it's a scale whatever the hell we want. This is 3 pi. This is omega, and this is your time. Divided by 280. So you want the units there. And the time here is in seconds. So here we go. So something like that. Alright. Then from 70 on, with a little dashed line like that, from 70 to 100, it's 0. And so we draw it on the line. Then it's 0 radians per second. So that's what our angular graph looks like. Okay. No slope here, no slope here. Right? That the change in slope is absolutely nothing, and that's visible from the graph that's right here on page 3. Right? We see that the increase is exactly the same for each of these. Okay, so that's why we don't have a slope there. And of course, if you guys are in calculus, you know that the slope of the derivative of a linear equation is of course a constant. So that should be recognized there. Okay. And the derivative of 0 is still 0. So that is something to keep in mind. Okay? So that's how we analyze. Our graph. For part B, to convert her radians per second into RPMs, we have 3 pi over 280 radians per second. We, of course, multiply that by the fact that we know that there's 1 revolution for every 2 pi radians. Pi's cancel. So whatever 28 times 2 is 56. So it's 3 over 256 of a revolution per second. And of course we know that there are 60 seconds for every minute. So it's times 60. So 3 times 280. That's not 256, by the way. That should be 560. And then 3 to 280 times 60. The 6's kill each other. And of course, 6 goes into that 3 times. And then 2 goes into that 14. And so we end up with 9/14 revolutions per minute. And that's how we do that. Okay? That's how we work with our angular. That's how we work with the angular speed and converting it to revolutions per minute. Okay. Let's move on. So, what happens in rotation is, of course, we have a circle. I want to be circle with its radius. And this is, of course, the angle, and this is, of course, the arc length. And if I'm rotating it through, I know that from the definition of the angle, I can get the arc length. And this arc length, recall, is the same as its linear distance between those 2 points around this curve. Right? It's the equivalent of its linear distance around the curve. So, what happens here, right? If I take the derivative of this position, it's linear derivative. Okay, the radius cannot change because the circle is equidistant. So this ends up being ds dt. Do not confuse it for the Nintendo DS, of course, which we should have. R remains constant because it does not change, and then d theta dt. Theta over time is, of course, the angular velocity. Distance over time is, of course, the speed. Distance over time is, of course, velocity, or you can consider distance, or you can consider its speed as well. So we get the equation, v is equal to r omega. And that's this equation here, which is the relationship between its linear speed and its angular velocity. Okay. So this is showing us the relationship linear speed and angular velocity. Or linear velocity, doesn't really matter because you have vectors in all situations. Well, the vector equation actually looks like this. Well, if we want to get fancy, the vector equation looks like v is equal to r cross its angular speed cross the angular velocity vector. But you can ignore that for all intents and purposes at this time because we're not working with the vector relationships yet. Okay? But there are important things you need to know about this equation. The first is that it only works in SI units. So the relationship is, of course, by the factor of R, which is true for all rotational quantities with the exception of energy and mass. And we'll talk about those later. Now, the important thing to note is that these must be in SI units. Right? So R has to be in meters, and the omega must be in radians per second. Okay. If it is not, the equation does not work. So it's something very important. The equation does not work if these two things are not true. Okay. It is only true in radians per second. It is not true otherwise, because there are other mathematical manipulations you must do in order to make it true. So keep that in mind. This only works with your SI units. Okay. This only works with your SI units. So keep it straight. Make sure you do not mess this up. Okay? We'll talk a little bit about that. Okay. So let's do an example involving this. Yeah, of course, nowadays we have our iPods with every little device on the. But this is back in the days when we had CDs. Okay. So we have the diameter, of a CD is, we'll make it a different number from what's in the book, 16 centimeters. Okay, 16.0 centimeters. Okay, so it's when the disc spins at say 720 RPM. What is the speed at the point So, the question asks, the diameter of a CD is 16 centimeters. when the disk spins at 720 revolutions per minute, what is the speed at a point 4 centimeters from the center and another point 8 centimeters from the center? Okay. So first, let's visualize it let's come up with a solution. So we need a solution. So we're going to visualize it. So to visualize it, we need to draw a CD. Okay. I gave you the diameter of this whole thing, which is 16 centimeters. Half of it is 8. So we know that point at 8 is at the complete outside of the center. And then from the center, I want to go 4 points, which is about halfway here. Okay. So there's a CD. There's as pretty of a CD as you're going to get. Okay. So this is our 0.8 centimeters outside the circle. And this is our 0.4 centimeters outside the circle. Okay. That's as pretty as it's getting. Now, the second thing, of course, we want to state what is given and what we need to find. So in this situation, what is given, we have its angular speed is, of course, 720 revolutions per minute, which we need to convert, of course, to radians per second. So to convert it to radians per second, we do that in this step here. We don't do it later, we do it right at the beginning. This way we don't mess it up. Okay, so revolutions per minute. So 20 revolutions per minute. Of course, there are 1 minute has 60 seconds. And of course, there is 2 pi radians for every rev. So to convert that really quick, that kills that. 72 divided by 6 is, of course, 12. 12 times 2 is 24. So of course, I could have also divided 2 by 3. I could have divided 2 by 3 and got 30. And then 72 divided by 3 is, of course, 24. So this is 24 pi radians per second. Give you a hint. It's making give you a hint. It's making 12 revolutions. It's taking 12 pi radians per second. 12 pi radians. So it's making 12 circles. 12 full circles. Now, we have the revolutions per second. We have radius 1. 0.0 centimeters, which is, of course, we need to convert it into meters, which we always do. Okay, we always convert our units into SI units whenever it's necessary. So there's 100 centimeters in 1 meter, so it moves it up back twice, 1, 2, so 0.04 meters. And I can just save you the trouble. This is 8.0 centimeters, which is 0.08 meters. From here, it's just a matter of multiplying. Okay. And so we need to find V1 and V2, which we'll do right here. So let's use a different color. Instead of the light blue, let's use this green color, I suppose. So we have V1 R1 omega, which is, of course, 0.04 divided by 24 pi, which, if you're really like me and a mathematician, you tend to do like this. You know that 2 divided by 5 is 40%, so 2 divided by 50 is, of course, 0.04, and it's 24 pi. And then you kill it. The 12, that becomes 25, because the 2's go away. So then 2 times 10 is 24 pi divided by 25. And you can leave that as such, and that's in meters per second. You can leave it as such because I'm an exactness and I like exact answers. And then for part 2, the same principle applies. We'll use the orange color this time. V2 is equal to R2 omega 2. By the way, it should be twice, just so you know. So it ends up equaling 0.8, which is 0.08 and 24 pi, which is of course 4 over 50. Behind a 24 pi. That kills that. 12.25, which is of course 48 pi divided 25 meters per second. And that's V2. Okay, so it should make sense that it's going twice as fast from the outer point than it is the inner point. And you can feel this, when you're going on your merry-go. You can feel it when you go on a merry-go-round. Even though you're both going exactly the same. You're both rotating at exactly the same rate. One side feels faster than the other. So we tend to sit on the outside if we want to feel like we're going faster than we want to sit on the inside. And we'll talk more about angular momentum later, which is more in detail what it talks about there. Okay. Okay. Now, recall that I've mentioned this before. Circular motion cannot occur without a force. Cannot, such. Right? And this is something we mentioned earlier when we talked about uniform motion. We'll talk about it again, but I'll remind you again that we talk about what we call centripetal acceleration, the acceleration that keeps things traveling in a circle around whatever point. This is my unpretty circle. This is my body, and it's traveling along this circle, right? Now it's being forced to stay in this circle by what we call, of course, centripetal force, which we'll learn more about that shortly. But this acceleration has to point towards exactly the center to keep this thing going in a circle. Otherwise, it of course will follow Newton's first law and go in a straight line. So we've spoken about centripetal acceleration before. Centripetal acceleration, A sub c, is of course v squared divided by r. And I know also that we learned earlier that v is equal to r times omega. And so we plug that in. And then we have that killing that. So we end up with r omega squared. An centripetal acceleration for that equation. This is a very important equation which you may wish to memorize, but you will not. So, in other words, what this is saying is that as your radius gets bigger, in other words, bigger radius, bigger centripetal acceleration. Smaller radius, smaller. In other words, it's harder for something, and you'll learn this later, it's harder to rotate it the closer you get to the center. It becomes harder to rotate. And you'll learn more about this when we get to chapter 7. But for now, you can keep that in mind, that the smaller radius will lead to a smaller centripetal acceleration. Okay? Okay. That looks totally unreadable, by the way. So I'm going to totally fix that. Centripetal acceleration. Now, so that's a little bit about that. Now, and of course you can see the example in your book about that particular point. And the last point I want to talk about before I conclude this point, I can conclude this lecture, before I conclude my point or conclude the lecture, we'll talk about quickly the causes of circular motion. Okay. Now, Newton's first law, recall what it states. So who wants to tell me Newton's first law of motion, and of which of course you're supposed to have completely memorized at this point, right? Newton's first law: in the absence of external forces, a body is at rest or at constant velocity. And this happens only when a body goes in a straight line, not when it's in a curved path, not when it goes in a zigzag path, but in a straight line only. And this is a very important thing, because if it's going in a curved path, there's always a force that allows this to happen. So that's what we're talking about here. In this situation, the only way for this force, for this object, this body, to remain in a circular path is that there's a force making this happen. There's a force keeping the body towards the center, or keeping it on its path. There's a force that's keeping it here. Now, there's a force making it stay towards the center. This force isn't... We need to be very careful about when we talk about centripetal forces. Centripetal forces can take the form of anything. There's no special real force called a centripetal force. It's whatever force happens to be pointing towards the center at that time. It can be gravity, it can be friction, it can be anything you want. Okay. It can be any kind of force, it can be a normal force, it can be whatever. It can be whatever kind of force you wish. But as long as it is pointing towards the center, this is what acts as a centripetal force. So make sure you keep that straight. There's no special force called centripetal force. The centripetal force takes the form of whatever force is pointing towards the center. So I'm going to write that because I talked a lot about that point. So centripetal force whatever force points towards the center. It can be gravity, friction, EM, whatever. Whatever force that points towards the center is what it will be. Okay, so you see on your text, so that's something very important to keep. Something to keep in mind when you're talking about this. Okay. And of course, we remember Newton's second law. Newton's second law states acceleration of a body is directly proportional to the sum of forces an inversely proportional to its mass. And if you need me to write that down, I gotta slap you. At this point, you need to linearize. So, since you have to linearize it, then of course, don't have to worry, I wouldn't actually hit you. Unfortunately, that would get you reported. That would get me reported, right? So we wouldn't actually hit you, but it's an expression, lest anybody get confused about that. So Newton's second law states acceleration is proportional to the vector sum of forces and inversely proportional to its mass. This is Newton's second law of motion. Oops, sorry, my M is not clear here. Okay, that's Newton's second law, and if you dare write F equals ma, you know what's going to happen to you. Now, of course, we talked about the centripetal acceleration. It will take this form as well, right? In this situation, right, there's always the force. In this case, it's the centripetal force. Whatever force is pointing towards the center that is acting in this acceleration. So we can say the centripetal acceleration is again equal to the vector sum of its forces over the mass. But there's a catch here, and this is something very important. I'm going to put this note here. I'm going to put it in the direction of our hat. What this is saying, okay, what that equation is telling you is something very important, that this acceleration is always, I'll put this here, towards the center. Okay, it's always directed towards the center of motion. So, and another way to write it is, of course, we can write it like this as well. I could write acceleration centripetal equal to v squared divided by r m. I can write it like this, which shows you a very unique relationship. Or I could write it as this. Both are correct in writing the two different forms of centripetal acceleration here. Okay. Please keep in mind, do not get it confused. It all depends on what's given to you as to what you'll do. Okay. Your textbook has it written as, of course, F equals ma, and whoever wrote the textbook ought to be shot because they got it correct when they wrote Newton's law earlier, and I don't know why they're not consistent, but gripes aside. So, again, the important thing to keep in mind is that the acceleration is inversely proportional to its mass. Okay. Acceleration is inversely proportional to the inertia, directly proportional to the vector sum of forces. In this situation, the vector sum of forces is directed towards what? The center. So this is why it's in the same direction. Okay? Alright, so that's just something to keep in mind. We'll talk more tomorrow about how to solve problems involving these kinds of forces. Okay. We'll talk more tomorrow about how to solve the kind of problems involving the situation. But I want to get us to keep in mind that the same rules for acceleration, the same Newton's law applies when I have centripetal forces, or when I have the forces that point towards the center. So, for example, I'm swinging a sensor, or I'm swinging like insensor, something like for Holy Mass. You know, I'm swinging it, and I swing it in full circle. Okay, the same rules apply. The only difference is now the radius is involved, and it gets a little bit tricky. Okay. So let's continue that. And tomorrow Well, actually, next week, because it's spring break, we'll talk about how to solve these kinds of problems.